The AI agent ecosystem, 90% engineering, 10% AI. Introduction, the hidden reality of AI agents. Welcome to a deep dive into one of the most misunderstood aspects of artificial intelligence today. When most people think of AI agents, they imagine sophisticated algorithms and machine learning models. However, the reality revealed by Rakeshko Hall's comprehensive ecosystem analysis is startling. AI agents are about 90% software engineering and only 10% AI. This revelation fundamentally changes how we should think about, build, and invest in AI agent technology. Let's explore this intricate ecosystem that powers the AI agents reshaping our digital world. The Great Misconception. Unlike traditional automation that relies heavily on conventional machine learning practices, AI agents represent a completely different paradigm. The infrastructure underneath tells a story that most don't see, a story of modular, industry-standard components working in harmony to create what appears to be intelligent behavior. Every component of AI agents is modular and industry-standard, which means we're not dealing with proprietary black boxes, but rather sophisticated orchestrations of proven technologies. This modularity is what enables the specialized companies we see across the ecosystem to focus on solving specific problems and improving scalable automation. The foundation layer, infrastructure and compute. CPU/GPU providers. At the very foundation of our ecosystem, we find the computational powerhouses. Companies like NVIDIA, AMD, Intel, and cloud providers like AWS and Google Cloud provide the raw processing power that agents require. These systems handle the compute-heavy processing necessary for training, inference, and latency-optimized execution. What's fascinating is how this isn't just about having powerful processors, it's about having the right kind of processing for different tasks. Training might require different computational approaches than real-time inference, and the infrastructure must adapt accordingly. Infrastructure and base systems. The next layer involves the scaffolding that keeps everything running smoothly. Infrastructure tools like containers and orchestrators ensure scalable, reliable, and distributed agent deployment. Think of companies like Docker, Kubernetes, and various cloud orchestration platforms. This layer is crucial because AI agents don't operate in isolation. They need to be deployed, scaled, monitored, and maintained across distributed environments. Without robust infrastructure, even the most sophisticated AI models become unusable in production. The data backbone. Database systems. AI agents require lightning-fast access to data systems that maintain memory, retrieve context, and enable real-time decisions. This involves both traditional structured databases and modern vectorized data systems. Companies specializing in vector databases, graph databases, and high-performance data retrieval are becoming increasingly important. The agent's ability to quickly access relevant information often determines the quality of its responses and decisions. ETL platforms. Before data becomes useful to AI agents, it must be collected and refined from various sources into usable formats. ETL platforms handle this crucial transformation, taking raw, messy data from multiple sources and converting it into clean, structured information that agents can effectively utilize. This pre-processing step is often overlooked but represents a massive engineering challenge, especially when dealing with real-time data streams that agents need to process continuously. The cognitive core. Foundation models. Here we encounter the 10% that most people think represents the entirety of AI agents. These include large language models, SLMs, and specialized foundation models that form the cognitive core of AI agents. Companies like OpenAI, Anthropic, Google, and others provide these models which power reasoning, dialogue, and decision-making capabilities. However, as our ecosystem shows, these models are just one component in a much larger system. Model routing. One of the most sophisticated aspects of modern AI agent systems is model routing, the ability to direct tasks to the most appropriate model based on cost, latency, and output quality requirements. This optimization layer can dramatically boost efficiency by ensuring that simple tasks don't consume expensive computational resources meant for complex reasoning. The orchestration layer. Agent protocols. This is where things get particularly interesting from a software engineering perspective. Agent protocols define how agents interact and communicate with each other. Protocols like MCP, A2A, and ACP facilitate structured multi-agent collaboration and context management. These protocols are essentially the languages that allow different agents to work together, share information, and coordinate their activities. It's pure software engineering, defining interfaces, data formats, and communication standards. Agent orchestration. Beyond individual agent capabilities, modern systems require agents to execute complex workflows, interact with other agents, and coordinate across various tools and environments. This orchestration layer manages the complexity of multi-agent systems and ensures that different components work together seamlessly. Security and governance. Agent authentication and authorization. As AI agents become more powerful and autonomous, security becomes paramount. Agent authentication handles secure identity validation, access control, and role-based permissioning for agent actions within trusted ecosystems. This isn't just about preventing unauthorized access, it's about ensuring that agents operate within defined boundaries and can be held accountable for their actions. Authentication systems. Protecting agent operations requires sophisticated identity validation and user access control layers. This includes both technical security measures and compliance with various regulatory frameworks. Monitoring and improvement. Agentic observability. One of the most critical yet overlooked aspects of AI agent systems is observability. This involves tracking agent behavior through telemetry, logs, feedback loops, and analytics for continuous improvement and debugging. Unlike traditional software systems, AI agents can behave unpredictably, making comprehensive monitoring essential for production deployments. Companies specializing in AI observability are becoming increasingly valuable as organizations scale their AI agent deployments. Integration and interaction. Tools and APIs. AI agents derive much of their value from their ability to interact with external systems. This includes APIs for data retrieval, search capabilities, and various external utilities that agents use to retrieve live data, automate decisions, and integrate across different domains. The richness of an agent's capabilities often depends more on the breadth and quality of its tool integrations than on the sophistication of its underlying AI model. Memory systems. Agents need to store previous interactions and contextual knowledge to provide personalized experiences and adapt over time. Memory systems represent another significant engineering challenge, involving decisions about what to store, how to retrieve relevant information quickly, and how to manage the growth of historical data. Front-end interfaces. Finally, users need ways to interact with AI agents through web applications, chat interfaces, and other UI components. This front-end layer must be intuitive, responsive, and capable of handling the dynamic nature of AI-generated content. The modular reality. What makes this ecosystem particularly interesting is that not all technologies shown are required to build an effective AI agent. The modular nature means that organizations can pick and choose components based on their specific needs, budget constraints, and technical requirements. A simple AI agent might only require a few components, while a sophisticated enterprise system might leverage the entire ecosystem. This flexibility is what's driving the rapid growth and adoption of AI agent technology across different industries and use cases. Industry implications. The 90% engineering, 10% AI reality has profound implications for how organizations should approach AI agent development. For businesses, success in AI agents isn't just about having access to the best AI models, it's about having robust software engineering practices and infrastructure capabilities. For developers, building effective AI agents requires full-stack engineering skills, from infrastructure management to user interface design. For investors, the most valuable opportunities may not be in AI model development, but in the specialized engineering tools and platforms that make AI agents practical and scalable in production environments. For organizations, implementing AI agents successfully requires significant engineering resources and infrastructure investment beyond just AI expertise. Conclusion: reframing AI agent development. This comprehensive ecosystem view reveals that AI agents represent a fascinating convergence of artificial intelligence and sophisticated software engineering. While the AI components provide the intelligence, the engineering components provide the reliability, scalability, and practical utility that make AI agents valuable in real-world applications. Understanding this 90-10 split is crucial for anyone involved in AI agent development, deployment, or investment. The future belongs not just to those who can build better AI models, but to those who can engineer better systems around those models. As we move forward, the companies that succeed in the AI agent space will likely be those that excel at both the 10% AI innovation and the 90% engineering excellence required to make that innovation practical, reliable, and scalable in production environments.